Scott, thank you so much for speaking to us today on World Quantum Day. The purpose of World Quantum Day is to increase the public awareness and understanding of quantum science and technology. And as I'm sure you encounter day in, day out, it's a notoriously hard and difficult concept to grasp. So I wanted to start this interview really by asking you in simple terms to describe what quantum is in your mind.
Yeah, so I think the way we view it at Aegiq is that, so we build quantum computers. And sitting behind that is that there is a fundamentally different way to build your computing stacks. So we became very used to carrying around computers in our pockets, using them every day, using for this call. But the way they operate is very different to how a quantum computer works. And really, it's less about how the operational system actually is implemented. You hear lots of fancy terminology around superposition, leveraging entanglement, et cetera, et cetera. But basically what it means is it uses a different rule set to operate. And once you can implement that, the things that you can calculate and you can do with these computers are vastly different to what we use today. We often talk about intractable problems, things that fundamentally we can't do in current computers. But for us, what that really means is building a computational capability that can simulate quantum mechanics as it is. And it can be things around materials discovery, it can be things around chemical engineering, where there are fundamental problem sets that operate in a quantum way that a classical computer can never simulate without huge approximations. What a quantum computer could do is it can natively map these into this rule set, and you can simulate, you can iterate, you can learn, and you can discover in a way that we just don't have access to date.
Okay, and what kind of applications do you envisage quantum being implemented into, and what kind of problems could it potentially solve?
So I think there are things that we know that quantum computing can solve at scale. There are algorithms that we understand that could be implemented once we get to these large-scale systems. But for us as a company, it's really around what we call quantum native problems. So this can mean, as an example, if you're designing an alloy system that needs to operate in particular conditions, historically what you may do is just build and iterate and test and see if it can function. But actually, what quantum computing can do is you can simulate from first principles. And this might mean in a jet engine, if you can operate the system at 100 degrees hotter, you can reduce the fuel consumption per flight of a couple of percent. And to do that, you need to have a turbine blade that can operate within that paradigm. But what quantum computing has the potential to enable is that rather than test and iterate and build, we can assemble these simulations from first principles and make estimations on the material compositions that can solve these problems that can go after these large commercial opportunities. And that could be things like catalysts in chemical engineering, lots of material science applications. And the way we view quantum computing, it's really like a multi-physics simulation tool taken to the extreme, that you can simulate things as they are to make predictions on things and how they would operate. And it opens this huge box of knowledge that we just don't have access to.
And what's the difference between what already exists? So you've already got multi-physics simulations. How big is that next step that quantum will take you on?
So it's more around how things currently operate. So you're constrained, and you're really constrained by the fact that certain problems, when you start going after certain complexity in them, they scale really poorly in current computers. So the world's biggest HPC centers, the Frontier system in Oak Ridge National Labs, for example, there are calculations and simulations, iterations on certain problem sets that you just fundamentally can't simulate. And the point is that in a quantum computing system, you can map it one-to-one directly. You get this exponential increase in your computational resource. And what that means is you can solve problems that are just currently intractable.
Yeah, and you mentioned jet engines there as one example, and being able to save fuel and essentially save carbon dioxide emissions. What are some of the bigger issues that you're looking at, or certainly the quantum industry are looking at in terms of societal changes and big impact things? I know things like medicines discovery is talked about quite a lot in parallel with quantum.
Yeah, absolutely. So it's any problem that can be natively mapped into these systems. So anything that requires deep insight from those fundamental molecular interactions. So pharmaceuticals is a good example. Obviously, drug discovery is well known for being a long, complex process, very iterative. If you had a tool whereby you could request to design a system that has particular properties, you could imagine a large-scale fault-tolerant quantum computing system being able to go at all the millions of different options that you could pursue to select a small shortlist where you're accurately predicting that this will have this capability. And you can think of that in terms of reducing the time to market. You can think of in terms of reducing the cost of development. But I think the really exciting thing is that the knowledge that will be gained, that it's not necessarily about cost reduction and time reduction. It's about that there are implementations that we just don't know are possible today because we don't have the tools to make those predictions. And I think those of us operating quantum computing see that this is almost like a new age of discovery in terms of humanity's knowledge about what we can build, how we can build it, and what we could pursue. And I think that while we are just currently scratching the surface, the coming decades will be dominated by innovation driven by quantum computing.
Mm-hmm. Yeah, absolutely. And I think naturally we'd like to talk about semiconductors as well in this story. And I'd be interested to get your take on the role of semiconductors in quantum and how the two industries, technologies intertwine with each other.
Yeah, so at Aegiq, so our thesis ultimately comes down to kind of one statement that in the history of humanity, we've only really been able to manufacture millions of anything in a couple of technology. And the first is probably kernels of corn in the agricultural revolution, and the second is transistors being manufactured at scale in the semiconductor industry. So our view is if we want to build a technology in computing that can scale to be deployed, ultimately the foundations that it must be built on are the semiconductor industry, that we need to leverage the trillions of dollars that have gone into these hugely complex processing foundries that are required to build these systems and use this investment to build the next generation of computing technologies based on quantum. And I think that it's only because of the maturity of the semiconductor industry that quantum computing is currently emerging as a capability that we believe we can engineer. And it's taken us 60, 70 years from the first transistor to get to where we are today, where we're thinking, well, actually, we can repurpose these technologies to build the next generation of compute. But it's really piggybacking on this huge investment in the semiconductor industry and the capabilities that we have there.
Yeah. And what does semiconductors inherently give you that you need in quantum or to do quantum?
Yeah, so I mean, a couple of things. So the scale needed to manufacture is quite a critical piece. That if you want to build and deploy systems, I mean, everyone's got a smartphone in their pocket, right? The way we talk about is often in principles called REV. So reliability, uniformity, reproducibility, and functionality. And if you want a technology to deliver that capability, semiconductor manufacturing is absolutely critical to it.
So let's talk a bit about you and how you kind of got started in this industry and kind of your time before Aegiq and how you got into co-founding the company and to where you are now.
Yeah, so I did so the company itself spun out from the University of Sheffield. So 16 years ago, I did a PhD in foundational technologies for quantum computing, particularly on quantum light sources, etc. And at the time, you know, it was an indulgent PhD pursuit about interest in the technology. And that kind of led to various levels of maturity in where we were. Then I took a slightly divergent route that I left the physics kind of academic route, and I went to industry for a few years. I worked at one of the catapult centers, the AMRC, and really that's about working with end users in the aerospace industry to take early stage technologies, take them through the valley of death and deploy at scale. And I learned a huge amount on the difficulties associated with that, but I maintained a lot of kind of contacts in my own research group. And I really felt that I understood the kind of process of taking this technology to commercialization. And then we reconnected with the old research group and spun the company out in 2019.
Mm-hmm. Great. And before your PhD, as the field of electronics, physics, quantum always interested you? What kind of got you into that whole industry in the first place?
Yeah, so interestingly, so I made a decision to do physics at university as an undergrad. So I also did this at the University of Sheffield. And my motivation is I wanted to work on one of these foundational problems that have a technological solution to something quite big. And I always kind of steer my career kind of along two lines in those early days. I either wanted to work in fusion research, which solves an intractable problem with huge benefits for humanity, or I wanted to work in quantum computing because of the promise of what it can enable longer term. And I kind of veered to the right. And then my decisions in and around that have all been around, well, how do we enable this at scale in the future? And I did veer out of academia for a time, but that was really about learning, well, how do you take low TRL research and deploy it at scale? And I think this is something as a company that we're doing now in the semiconductor quantum industry.
Yeah, absolutely. So talk to us a bit about Aegiq then. So 2019, I think you said, spun out of Sheffield University. Give us a little potted history of where you went from there and how you've got to where you are today.
Yeah, so at Aegiq, we build quantum computers using light. So we use photons, and we do that using semiconductor chips. So the company was assembled based on a number of breakthroughs coming from the University of Sheffield's physics department, and also the National Epitaxy facility that's here in Sheffield that forms the Sheffield Quantum Centre. And really, there was a fundamental bottleneck associated with building photonic quantum computers, that we didn't have very good light sources, basically, to generate these photonic qubits. So what happened within the old research group is they developed technology based on a compound semiconductor platform that could natively emit quantum light in the communication bands for telecom. And the feeling here is that we've solved a fundamental problem within the tech stack here, that now it's about execution and building systems around that. So since then, we went on to raise a pre-seed round in 22, a seed round in 24. We've expanded the team to now 28 people, still headquartered in Sheffield. We've deployed a first-generation system at the UK's National Quantum Computing Centre, which is a fully active, deployed photonic quantum computing system, and received further support under the quantum strategy, with our second-generation system currently being developed under the UK's quantum mission pilot funding.
Fantastic. And I think we'll talk a bit more about that scale-up journey in a little bit. But going back to the technology, you mentioned that you're working on a photonic quantum technology. Now, I know you've talked in the past about different modalities and different ways of doing it. Why did you choose this way? What's so special about this way? And kind of what is the big problem that you're trying to solve?
Yeah, so the interesting thing in quantum is that there are many, many different approaches being pursued across the world. And it really comes down to kind of what the thesis is behind your technical decisions. So our view is that, what do we care about longer term, the economics of the solution? We care about an ability to deploy. We want to be able to take these systems and install them custom premises, ideally in data centers, HPC centers, and on-site. And we picked photonics because essentially it doesn't require any of the complex cryogenics, extreme environments. When you see an Aegiq system, you won't see a dilution fridge, one of these large chandeliers that cool to millikelvin. You'll see 19-inch racks, modular systems that are all interconnected with optical fiber. And that allows us to have a robustness in the deployment that we believe you will require ultimately when the technology is developed. The second point is really about scalability. And that means two things. The first is you've got to be able to scale your manufacturing to deliver systems at scale that fundamentally work. And all of our photonic chipsets are built on semiconductor foundry manufacturing. We don't require any exotic materials, and we can repurpose the technology that's being used to manufacture the chips in your phones and computers. But the final aspect is that we all have qubits. And the problem in quantum computing is we all have high-performing qubits at the moment. But we need orders of magnitude more of these if we want to go after some of these interesting and tractable problems. And what photonics allows you to do is to interconnect via optical fiber. A little bit how HPC is being scaled out in GPU clusters in data centers via optical connection between clusters. Essentially, photonic quantum computers allows you to leverage exactly the same scale-out techniques. So the power behind photonics is that you can manufacture it, you can deploy it, and you can scale it very quickly. Based on these strengths, and because of this, we pursue this modality with our clear strategy.
Yeah, and I was reading as well that on your website that you say your systems are designed to work in parallel with data centers or alongside data centers and GPUs and AI infrastructure. Can you tell a bit about how that would work? Because me being quite naive and not knowing too much about the subject, I always thought that quantum and classical computing were very different and gave you different results. But are you saying that they could potentially intertwine and work together?
Yeah, so I mean, there's many aspects of this. So our view is that quantum isn't coming to replace classical compute, it's coming to complement it. You'll still require your classical computation, your CPUs and your GPUs to do certain aspects of your calculation, and quantum processing units or quantum computers will look after the aspects of that workflow that are natively quantum. And that means that actually what you want is what's called hybrid. You want access to quantum computing, you want access to GPU acceleration, the graphical processing units of NVIDIA and others, but you also want access to the CPUs. And actually any useful quantum computing system will be an admixture of those technologies working across kind of synchronization of these particular problem sets.
Yeah. Okay. And you talked a bit about your technology being able to produce these qubits and these photons. Can you do the end-to-end whole computing stuff with your technology, or do you envisage yourself being that starting point of a wider system?
No. So we build full stack systems. We do end to end. So in a photonic quantum computer, we talk about 4 pillars. So you've got to create your photons, your entangled states will whiz through the system. You need to be able to switch them around. You need to be able to process them and detect them. And our systems incorporate all aspects of this, each one with a particular semiconductor chip. So what we do uniquely is we use on-demand sources of quantum light to miniaturize the systems. And actually, our architectural approach, which we published late last year, is really an optimization of what the blueprint for a large-scale system would look like, with the ability to on-demand generate the photon inputs that you need to do to have this system. And really what that allows us to do is to miniaturize and have a lower footprint and lower cost associated with our systems compared with what's been pursued historically.
Okay, great. And I understand you're working with quite a few UK companies as well on your technology in terms of tape out and developing your chips. Is that correct?
Yeah, so we have, so one of the things that we have, we're leveraging aligning the UK sovereign capability. And a big aspect of this is really leaning into the South Wales compound semiconductor cluster. Under our quantum mission pilot funding, we have a collaborative co-development project with IQE, where we're transferring the technology on our light sources to their facility in the South Wales region to be able to be a longer-term supplier. Obviously, IQE provide a lot of compound semiconductors, a variety of industries, but actually we can adapt this to be able to deliver quantum light sources at scale. We have a very long-standing collaboration with the team there.
And was that a conscious decision you made at the very start of Aegiq to try and use sovereign capabilities and technologies? And if so, why is that important to you?
I think it's an admixture of reasons. I think the first is that the UK has key strengths in certain areas of semiconductors that make a lot of sense for us to continue to invest in and to leverage as a company. And the big one for us is that world-leading expertise exists within the compound semiconductor ecosystem, so it's a natural fit for us to then be able to manufacture this at scale. But I think the importance in the UK is ultimately, it's about resilience and reliance internationally, that quantum is going to be a technology where sovereign capability is key towards what the next generations of technology are going to look at. And the opportunity presented within the strengths of the ecosystems that we have should be positioned in a way to contribute to the delivery of those systems. So I think that there's the kind of intersection between our requirements and the capabilities in the UK. There's also a sovereign aspect of things that ultimately, if the UK wants to be a leader in quantum, it needs to be a leader in the semiconductor manufacturing base to be able to enable that sector. So I think both are kind of run hand in hand in terms of our thinking around how we build this longer term.
Yeah, and it's quite, it feels like quite an exciting time for quantum in the UK at the moment, with lots of investment coming from government and clear signals that this is an area where we truly are world leading, and we're seeing lots of companies doing well, funding wise, but also in terms of kind of business performance as well. Do you see that from inside the industry as well?
Yeah, absolutely. I think the UK was the first to move with a coherent strategy under the phase one. And what this did is it transferred a lot of the world-leading expertise in universities into companies. And we've just seen in the past month the announcement of what the phase two strategy looks like, a 2.5 billion commitment across the next decade, a rigorous procurement program aligned to equipping the UK with world-leading capability. And I think the industry has welcomed this with open arms in terms of government investment to de-risk. And I think what this has created is probably one of the most exciting ecosystems internationally in terms of capability and breadth of knowledge across the different approaches as well. And what that's led to is lots of investment inward into the UK for companies like us to be able to build and scale here and actually be a UK sovereign champion. Our view is within the UK quantum capability, there is an opportunity for large companies to be built here. And actually the UK government's commitment is one of the key enablers to being able to de-risk that journey for us to stay in the UK and continue to scale.
Yeah, absolutely. I think that's really important is how you keep these companies here and keep them scaling. And it'd be great to talk about that scaling journey, actually. So you mentioned a couple of rounds that you've been through so far. How much have you raised to date, and talk us through that process?
Yeah, so since the company inception, we've raised around £8 million worth of equity investment across a pre-seed and a seed round. And then that was topped up with funding under the quantum program. So we were awarded a number of contracts in the government to deliver certain capabilities, one being the UK, the National Quantum Computing Centre deployment, alongside investment in kind of core development around CRDs and grant funding. So all in, we've had around £16 million worth of investment in the company at the moment. We're just in the process of closing our Series A raise, which will be well further investment. We're actually just investing in a large new facility here in Sheffield. So this is the office we're just moving to today, in fact. And this allows us to scale to 65 people, invest further into the ecosystem, and continue to expand once we've closed our next round of funding.
Yeah, that sounds great. And what's it like scaling a quantum company? Do you find that, in terms of investment and speaking to investors day in, day out, are they bought in because of the amount of attention that it's got, or is it still quite difficult in terms of the complexities? Is it a difficult sell? Do investors need to take that leap of faith?
I think it's an interesting one. Our experience is that there's a lot of excitement of what this means in terms of the longer term market opportunity of value capture. There seems to be a wide acceptance that the computational journey we've lived through the past 60 years is going to end up in quantum computing, and the market that will unlock will be enormous. So I think investor sentiment is quite high. And I think the UK government's commitment to de-risk a lot of the technological development via the programs is being quite critical to get significant investor investment into this sector. But I think our view is that there are a few complicated challenges that sit in front of humanity in terms of its ability to develop technology, and quantum computing sits at the forefront of this. And because of this, I think there's a lot of excitement around what it could be, what it will achieve, and what it could unlock for us as a nation.
Yeah. Talk to us a bit about the investors. Where have they come from? Have they been mainly in the UK or internationally?
So internationally, so we're backed by a number of UK-based investors, also by European and also some US funding. So I think quantum itself attracts investment from international based investors.
Yeah, that's fantastic. And have you noticed a difference between speaking to various investors from different countries? Has there been kind of variations in the pitch or the response from investors?
I think that it varies depending on the specifics of where you're pitching and who you're pitching to, on what the belief in the opportunity could be, and perhaps the risk appetite associated with this, and the steps along this. Obviously, it's well known that in the US, there's a quite a different mentality regarding the approach to venture capital and investment. So some adaptations must be made in terms of where the ambition needs to lie. But I think overall, it's been relatively consistent in terms of the messaging and the receipt of that messaging.
Yeah, great. And we've talked a lot so far about Sheffield, where you were from, and where you spun out from. I'd just be interested to know a bit about the ecosystem in Sheffield and how that's helped you, and why you're still there and you're scaling and opening a new office in Sheffield now.
Yeah, so I think we are uniquely the only UK-based quantum computing company based in the north of the UK. And that was a conscious decision when we spun the company out. And really what it comes down to is access to talent. We've got a fantastic semiconductor and quantum capability in the universities here, and we hire a lot from this ecosystem. But Sheffield itself has a exploding deep tech sector. I think in the recent years, there's been around 25 spin-outs and startups coming into the ecosystem, really trying to build in scale. And actually, our view is there's quite a unique opportunity amongst the northern cities here, where the economic benefits are disproportionate to where typically you might start companies like this. And a lot of that has been around, graduate recruitment, the choices that people are making about where they want to live, and the access to opportunities. And actually what we're seeing in Sheffield at the moment is a huge clustering around deep and hard tech. So we are not the only quantum company in Sheffield, for example. There are others working in cybersecurity aspects. There are companies working on detector technology, and other companies working on micro LED technology that have been spun out and scaling in the city. And actually, there's a huge amount of momentum at the moment about founders and entrepreneurs choosing to build rather than follow those traditional routes. And this anchors a lot into the history of Sheffield as well. Just outside the city is the Advanced Manufacturing Park. And people often say, well, what about the choice about why be in Sheffield? And we would say, well, the biggest beneficiaries of quantum computing at scale are those operating in material science, operating complex aerospace. And actually just, 20 miles from where our office is based, you've got Rolls-Royce's advanced blading casting facility. You've got Boeing's only European factory for manufacturing in Europe. You've got McLaren that manufacture carbon fiber weave tubs. And actually there's a burgeoning ecosystem of advanced industries that are sitting in this sector that we believe will be long-term beneficiaries of the technology that we're developing.
Yeah, it goes back to your first answer, doesn't it, about your use case of developing materials and advanced materials using quantum computing and quantum techniques, and having those on your doorstep and ready to literally knock on that door. I think is quite an exciting prospect, it sounds.
Yeah, absolutely. And I think the benefit of being here is that you get access close to those people, so be the biggest beneficiaries of it.
Yeah, absolutely. And you say there's lots of startups and spin outs happening around Sheffield. I'd be interested to get kind of your advice, having been through that process over the last, say, 8, 9 years. What type of advice would you give to spin outs and startups in the UK?
I think the opportunity is there. It's about building resilience and belief in what you're doing, and taking that leap of faith to be able to deliver. I think that the journey that we've been on, we've had a lot of successes, and obviously as part of that journey there's a lot of difficulties. But ultimately, it's about navigating with belief that you are doing something with a clear mission vision, mission focus, while solving a useful, relevant problem that will be beneficial in terms of markets, humanity. And if you've got those kind of North Stars aligned, then it's about building the resilience to keep grinding at the coal face every day to get to the point that you want to deliver.
Yeah, absolutely. And I think I've spoken to you a couple of times now, and what always impresses me is your kind of business knowledge as well. And you talk very well in a business sense about Aegiq and the environment you operate in. I'd just be interested, kind of, is that something you've always been interested in or something you've had to develop quite quickly on the job? And I always find that very impressive from founders and spin outs, that you have to kind of keep going on that technological journey and you keep innovating and being an engineer and being a scientist, but at the same time, you've got to be talking to investors and running a business. I just like to get your kind of view of how you balance those two things.
Yeah, I think that fundamentally the thing you've got to be motivated by is solving business problems. And when we talk about quantum computing, the enabling technology, it's very easy to get really excited by the depth of technological complexity associated with those implementations. But ultimately, it's serving a purpose. And the purpose it's serving is about solving commercially relevant problems for our customers. And actually, the foundation of the business for me was a lot about the motivations around some of the experience I had in the aerospace sector, where we were coming across problems where I was assuming there would be a computational solution to simulate, iterate, develop, and there wasn't. And I think that deep-rooted frustration really maps onto kind of the problem solution that we have at Aegiq, and why we're so motivated that ultimately we are developing technology to solve commercially relevant problems and solve products into this, which is very much anchored around the technological developments. And the technology's got to serve the purpose of the business, not the business serving the purpose of the technology.
Yes. Yeah. And do you enjoy being a CEO, co-founder? Do you enjoy running a business and that side of things?
Yeah, so I'd say it's the most rewarding job you could have.
Mhm.
But you've got to have the resilience to keep pushing. And I think the thing that really matters the most is like an ability to hire outstanding people. And I would say a lot of the success of Aegiq is down to the early ability of the founding team to attract exceptionally capable people to the business. That a lot of Aegiq success isn't down to those that started the company. It's basically those that were able to attract and continue to attract to be able to iterate and build on what we start with this foundation is. I would say my role is to ensure that we have the resources to deliver, the operational capability to deliver, and to be able to attract the team members that can then execute on that roadmap. And we have fantastic people here that continuously innovate, develop, and iterate to the point where we're able to deliver on the promises that we've made over recent years.
Yeah, that's fantastic. That's great to hear. And people is such an important part of business, isn't it now? And certainly within quantum and semiconductor industries, we talk a lot about skilled workforce and a gaping hole in the next 10 to 15 years. So it's great that you're able to, you have that pipeline there in Sheffield by the sounds of it.
Yeah, absolutely.
Great. Well, one final question, and that's about the future. So what are your future plans for growth, and what's next on the agenda for Aegiq?
Yeah, so we are just opening our new facility in Sheffield. So this is a big commitment to us to stay up in the Northern ecosystem, and we'll be expanding rapidly. We're currently just under 30 people full time, and we'll be expanding to around 60 over the next 18 months, aligned to our Series A close. And really, it's about building our next generation systems. You'll hear a little bit more of this as we announce over the coming months. But we have a architectural approach which we believe has a pathway using semiconductor manufacturing to deliver capabilities of commercial relevance, and we're currently building those systems today. So really, it's about executing on our roadmap, expanding the team, and continue to innovate and iterate with our customers.
Fantastic. Well, that sounds really good, and certainly here at the UKSC, we look forward to following that journey and following you closely and working with you closely as well over the coming years. Scott, I wish you a happy World Quantum Day. Thanks very much for talking to us. And best of luck for the future.